60% of CO2 emissions can be attributed to supply chain activities. As an optimization expert, you want to work for a purpose. You want to improve the efficiency of our supply chains, take waste out, and reduce unnecessary expenditure on transportation, emissions, etc. Problem is, no one in supply chain is listening to you. Today we'll discuss why that might be. Particularly, we're going to look at an example that was put out by one of our main competitors, Gurobi, on distributing and pricing avocados, and how that example is undermining the credibility of everyone working in optimization. We need to talk. So let's have a look at this use case that is the topic of this Gurobi notebook. What we have here is an avocado producing company that produces avocados and distributes these avocados to 8 different regions in the United States. They need to set the prices for the avocados, and of course they have to supply each area with sufficient numbers of avocados to then sell them. There are transportation costs involved. The further away from the port, the more it costs to ship the avocados. The objective here is to optimize net revenue. So this is the revenue after we're subtracting the transportation costs and also the cost for disposing wasted avocados, which are assumed to cost 10 cents a piece. So this is what this notebook is about. The first thing that they do is they download Kaggle data. This was actually this forecasting the amount of demand that will be created at a certain price was the topic of a Kaggle competition. Gurobi here augmented this with data that they privately obtained from this avocado seller. So we are looking at the price sensitivity forecasting. How many avocados am I going to sell in each region, given that I'm taking a certain price in that region. And now there's a bunch of data analysis that gets done here in this notebook, which isn't particularly interesting. I added a visualization of the final fit that we're getting here. So Gurobi uses an ordinary least squares algorithm in order to fit a linear regression to the data. And here we see kind of how that data errs. So at a particular price, we are forecasting a particular demand. And here we're comparing the actual demand in million avocados with the predicted. And we see that, yes, there is a reasonable fit here, but of course it's far from perfect. Now, Gurobi makes 2 mistakes here. The first one is they actually use the whole data in order to train this model, and then they evaluate their optimizer on it. That is like the cardinal sin that you learn in your very first machine learning course that you cannot do, to use data that you used for training in order to use it for testing. Then again, it is such a crude model to use a linear regression for this task. That plus it isn't really about the fit of the forecast. It is about the question of how well can we use those forecasts in order to make good decisions in terms of how many avocados we're supplying each region with and what price we're going to set in each region, that it can be somewhat forgiven. What can absolutely not be forgiven is the fact that Gurobi completely ignores that, of course, there is residual uncertainty here, right? All of these examples that you're seeing here do not fall on this main diagonal. There is a spread, right? For an actual value, we're going to get a whole spread of predicted values. And for predicted value, we're going to get a whole spread of actual values. So we do not actually know how many avocados will be demanded at a given price. There's uncertainty around it. So what does Gurobi do? they build an optimization model here where you can see that minima and maxima on the price as well as the avocados are being set. The number of avocados that we need to distribute is given to us. This is kind of the capacity that we have of avocados, but then again, they're all produced, so we also need to sell them, otherwise we waste them. And we do what we would do, right? So the objective function is the price times the number of sold avocados minus the ones that weren't sold times the 10 cents per avocado waste. And then there's transportation cost per avocado that ranges anywhere between 10 cents and 50 cents per avocado. This model gets built out. Constraints are being set here so that the sales and the waste are being computed correctly. Then we fire up the solver, and the objective function here, of course, is convex because it's not linear. It's because the sales and the price are both variables in the Gurobi model. And so this is a quadratic term that you have over here, but it's nicely convex, and really these problems solve very, very easily. But of course, in order to compute how much gets sold, Gurobi uses the demand forecast at the given price that was chosen, as if it were set in stone and had no uncertainty around it. And that is exactly the issue that we're going to look at today. So now that we run this, what we're going to get here in this one example, so they took out 1 week, you get this solution over here. And when I'm talking about undermining your credibility with folks in supply chain, if you want to successfully do that, all you have to do is show them this table. Because if somebody in supply chain sees that, okay, we're going to take in the Great Lakes region, we're going to take a price of 166, and we allocate 3.44 million to this region, and our optimizer expects that we're going to sell 3.44 million and have absolutely no waste, then the only way that this could possibly happen is if the price is so low that we are definitely going to sell out everything. But that would hardly optimize my revenue, right? If my price is so low that I'm guaranteed to sell everything, this means that my price is too low, right? So I have to kind of up the price to a point where I'm in the vicinity of what I actually have available. And clearly this is being done. The problem here that Gurobi thinks that they're going to sell this much, even though the price is high enough that my forecasted demand, the predicted demand, is 3.44. It's not massively higher, which is why we would be selling out. No, the predicted demand at this price is 3.44 million. And then I'm assuming that this is the exact number that will be sold. Then I'm forgetting two things. The first one is sometimes the demand is softer, in which case I'm not going to sell this much. And I'm going to have waste. And other times the demand is going to be much stronger. And I didn't know that, right? Many more people want avocados, and they don't care whether it's $1.66 or $1.75. They need their avocados, and they're going to buy them. In which case, you're leaving a lot of opportunity on the table if you are if you're only providing 3.44 million to this region. And this continues in every region that is there, except for the Mid-South region, where we have allocated, because we need to get rid of all of our avocados, presumably, where we put the entire excess that we have and put it in the Mid-South. Right? So here you see that the allocated amount here is higher than the predicted demand, and consequently we're expecting 1.7 million avocados to be wasted in the Mid-South, but everywhere else the waste is zero, and the number of sold avocados is exactly the number of allocated avocados is exactly the number of predicted demand. And now imagine that you're presenting these results to an experienced supply planner, they're not going to take you seriously for obvious reasons, because this entire worksheet is not understanding the nature of their business, does not understand that we cannot forecast everything perfectly, and all credibility is shot both with data scientists and supply chainers. We need to fix that, because optimization is too important as a technology not to be used in supply chain. We have to make the world a more efficient place. We have to help companies work more efficiently and more profitably, and we cannot do that if all we sell is deterministic optimization. So let's fix that issue. Let us begin by taking a more honest look at the results that we would be getting if we are using deterministic optimization. So particularly, I went into this worksheet. So what they do here is they build a function that solves these different MIPS, and then they go through the different weeks and try and set prices and allocate volume of avocados to different regions for each week. First thing I did is I do this for all the weeks. And since we don't have a train test split anyway, we might as well use the whole data set and not just parts of it. That way we can also see with more statistical significance on how much money we're actually leaving on the table by doing what Gurobi is doing. And then the other thing that I did is this. In the data, I have a price that the avocado sellers did set historically. And I see what the demand is for that. So I know in what week how my forecast deviated from actual demands. So I see what percentage of the forecasted demand actually got realized. And now there is, of course, the issue that you don't see the outliers to the top, because it's obviously capped by the allocation that was originally put into a region, which we do not know. So consequently, but we're simply going to take this at face value right now and say, okay, if actually more than expected sold historically at the historic price, say 10% more, then we will assume that at the price that Gurobi sets, we're also having 10% more demand. And consequently, if in a region the demand was softer, say only 78% of the demand was realized, then what would have been expected at the price that the avocado company historically set in that week, then we're also going to apply 78% to the expected demand at the Gurobi prices. And now we can compute how well Gurobi actually does. Right, so what we're doing here is exactly this, right? So if you look at this changed worksheet over here, we have an expected number of units that we would expect at the Gurobi prices. We have expected number of units, so an expected number for the demand for each region at the actual prices. And now we can see how much of that actually got sold, and we can compute this ratio of the two between the actually realized demand and the expected demand according to our learned model at the actual prices, and how big the demand actually was. And we're going to apply this realized demand to the expected demand that we computed from Gurobi. So we use the same factor here in order to do this, and then we're going to compute the whole thing, how well Gurobi would do. So the way how you can think about it is we're applying the exact same residuals, the exact same error that we're seeing in our training set, which is the test set here. As ridiculous this is for data scientists, but I wanted to keep this as close to the original sheet as possible, so that people see that this isn't fudged or anything, but they weren't 10 million parameters that we could set any which way we wanted in order to get the results that we do. So we're sticking close to the original notebook, even though you don't want to show this to a data scientist. But the advantage, if you have the data set, the train set be the test set, is of course that in the training set you see exactly the residual errors that you are having, and we're applying them, plain and simple, to the forecast at the Gurobi prices as well, in the same magnitude. And that way we get a much more honest assessment of how well Gurobi would actually be doing. With that ability to assess more realistically how well Gurobi would actually do, not in hallucination world, where the forecast is reality, but where reality can deviate from the forecasts, that enables us, of course, to now compare with other methods in order to solve this exact same problem. Set prices and allocate avocado volume to different areas. So we're going to build a seeker model to do the exact same thing. So here we follow exactly the approach that was also taken otherwise in the notebook. We build a function that can actually solve these problems. So what you see over here is, if you look at the stochastic model that we're using here in order to solve this problem, it works exactly the same way as you would expect. We are taking a percent allocation of the total available volume of avocados. So we get that. We're obeying the min and the maxes, so the constraints are the same. We're setting prices anywhere between $0 and $2 per avocado. And then, of course, we're going to get an expected demand, which you see here gets multiplied times a distortion. So what we did earlier when we looked at the fit of the linear regression with the actual data, we could compute mean percentage average, mean percent absolute deviation. And that was around at about 23%. So we're going to use that as a standard deviation of a normal distribution with expected value 1 and multiply the forecast by that linear regression times that noise factor that we're having over here. And like this, now within Seeker, we are getting a stochastic optimization problem. And of course, now when we optimize the whole thing, we need to take a statistic over what we want to optimize. What we're going to take here is the expected profit that we would be getting. And so you see here that we're running the whole thing here for 0.9 seconds, and we do an upfront deterministic optimization here. It's exact same model, but without the stochasticity to set initial prices. It's a good trick when you're doing stochastic optimization to initialize at what the deterministic would be, and then start the stochasticity from there. And so the whole thing takes a second per week that we're having here. Again, there's 196 weeks in the problem. And then we do the exact same thing that we're also doing to the Gurobi solutions, and distort what we would have expected at the prices that Seeker set, and apply the exact same residual error to those expected values, and then compute, well, how well would the Seeker solution have done. Now, if we do this, if we run this, we're getting this result over here. What you see here is all 196 different experiments where we go head-to-head between Gurobi and Seeker. The Seeker dots are orange, the Gurobi dots are blue. And you see for each week in the peak season, again, we didn't want to change the notebook more than we had to. So since Gurobi does the whole thing with peak season weeks only, we did the same thing. And you see here that by and large, if you're going vertical, you see that the Seeker solution is generally better than the Gurobi solution, particularly here in in year 2018. It's very, very clear that preparing for the uncertainty in the demand forecast at a given price is a very, very good idea. if you're taking these results here, so this is run at a second with, since this is a demo version in the notebook, in the Google Colab, we're somewhat restricted of what we can do. But even here, at just 500 scenarios for each, Seeker leads to $900,000 more in weekly net revenue than the quote-unquote optimal Gurobi. Over the span of this data, so all 196 peak weeks that we're having here, that results into $177 million more in net revenue for the company. Another way to look at it is, out of these 196 head-to-head comparisons, Seeker wins more than 2/3, so 136 in this case, which is more than 2/3 of all head-to-head comparisons. So now if you put everything together, Gurobi's claim of optimality, when clearly it isn't. Gurobi's claim to seamlessly integrate data science with optimization, while ignoring all uncertainty in the forecasts, while ignoring the most essential things like separating train and test. Then you do have indeed to ask the question that Gurobi posed at the beginning of their notebook. How much is too much?